What did we see out there? Well, we saw that the universe around us is pretty fixed in its shape. The stars maintain their pattern. And then we saw in addition that the entire pattern appears to rotate around us, moving from east to west. Now, we have a modern understanding of all of this. Of course, the modern understanding is that we live in a large three-dimensional universe. The stars are very, very distant, and that's why they appear to us not to move, because they're so far away that their motion is irrelevant. And the reason the entire fixed universe appears to us to be rotating from east to west is simply that we, living on the Earth, are rotating from west to east. And so, from our point of view, things appear to be rotating. If you think everything is spinning, it's probably you that are. And so, we live on this rotating spaceship Earth, and its daily rotation from west to east makes the universe appear to us to be rotating daily from east to west. Very nice. We have an understanding of what goes on. The picture that we see in the sky, however, is a two-dimensional picture. We do not have a good way of measuring or noticing the distance to stars. All stars appear to us to be essentially very far away, though how far will be a story that we'll have to develop later. Before we get there, at the level of just watching the planetarium show that is the heavens, what we need to describe is direction. So we may as well assume that all the stars are at one very fixed large distance from us. In other words, they span a great big globe surrounding the terrestrial globe. We call it the celestial sphere, and the positions of the stars are fixed on the celestial sphere because that is how they are. So here's Aristotle in 350 BC, looking down his nose at the ancients, who thought that it required gods in heaven to maintain the stars in their fixed positions and their regular periodic motion. No, says Aristotle, there are laws of nature that compel the stars to do what we see them doing. That is very much the spirit in which we will work, though we will try to take it a step further and actually understand those laws and comprehend them by making measurements down here on Earth, because our laws are going to be universal. For Aristotle, there is a set of laws governing terrestrial phenomena and a completely different set of laws governing phenomena in the heavens. But before we get to all of this, we need to describe the planetarium show, where it is that we see which stars at what time, how the whole thing moves. And for this, we can follow the mathematical model, which is what Aristotle is describing, which is this picture of the stars fixed on a large celestial sphere. Inside this sphere, the Earth rotates daily from west to east, or if you want, the entire celestial sphere rotates daily from east to west with the Earth fixed inside it. From the point of view of lines of vision, whether the celestial sphere rotates or the Earth rotates inside the stationary celestial sphere is a matter of complete indifference. The two are completely equivalent. So we have the celestial sphere on which the stars are fixed, and what we need to get a more precise mathematical description of where stars are is we need to be able to label points on the celestial sphere, because somewhere on the celestial sphere, say over here, is the constellation Orion. Somewhere on the other side of the celestial sphere, say over here, is the constellation Cygnus. You could say a star is in Orion, but if you want to be more precise than that, you need to say where exactly in Orion it is. We need a way of specifying positions on a sphere, or directions in the sky. Luckily, we know very well how to describe positions on a sphere, because, remember again, we live on a sphere. We use positions on this sphere all the time. We specify points on Earth by giving their latitude and longitude. Those are the coordinates on the Earth. Remind us what that means. Well, the Earth, because it spins, has an axis with poles, where the axis meets the surface, a north and a south pole. Splitting the distance between them is this great circle of the equator, and we measure latitude as the angular distance north or south of the equator, so that the North Pole is at latitude plus 90 and the South Pole at latitude minus 90, and picking a latitude gives you a particular circle, a parallel, say the 38th parallel. If you live at the latitude 38 north, you live somewhere along the circle. To specify where along the circle, we split the Earth into these orange slices with great circles passing through the poles. Those are lines of longitude or meridians. And if you know what parallel and what meridian you're on, that's a street address, and then we know where you are. Now, picking the zero of latitude was very natural. It was the equator that split the distance to the poles. Picking the zero of longitude is a more tricky business. We know that we measure longitude from this particular meridian, the prime meridian. What makes it prime is that it passes through the Royal Observatory in Greenwich, England. Of course, that's a political decision which tells us that there is no natural way to set a zero meridian. You just pick one, and then you measure longitude east or west of that in degrees, so that, say, Aristotle in Athens, Greece, is 37 point something degrees north of the equator and about 24 degrees east of the prime meridian. That specifies where Athens lies. Let's review in a minute what exactly we mean by this. So here's a model of Earth, and on this model I can add the poles because the Earth rotates, so I will orient the Earth as we usually do with the North Pole on top. And here are two diameters through the center of the Earth, the axis and another perpendicular diameter. Here is the Earth's equator, as best I can draw it, and we are going to place some observer at some particular point on the surface of the Earth, and the position of that observer is determined by measuring this angle, which is his latitude. And that determines a line of latitude, a parallel, on which the observer lives, but we need to specify which of the points on this parallel is the point occupied by our particular observer. Notice that this parallel is in fact the trajectory of the observer's motion as the Earth makes its daily rotation. The observer who is now here will 12 hours later be on the other side, and in general this is your trajectory as you move around the world once a day. And so to specify that, of course, we drew our lines of longitude, our meridians. We draw some meridians. And pick which one of these you live on, and that tells you where along this line of longitude you live. Now, where you are on Earth, of course, also determines, among other things, what it is of the sky you can see. So if you live at this particular point, then this roughly measures your horizon. You can see the half of the sky that lies above your horizon and not the half that lies below it. Your horizon changes as the Earth rotates. 12 hours later, you will see this half of the sky and fail to see that half of the sky. We have coordinates on Earth. We know how to specify coordinates on a sphere. Let's take this to the next level and apply the same idea to design coordinates on a celestial sphere. So here we have the model that I was describing. We have the Earth sitting in the middle of a large celestial sphere. You should imagine that the Earth is very small, the celestial sphere very large. Celestial sphere, inside the celestial sphere, the Earth rotates from west to east, or equivalently, the celestial sphere rotates from east to west. Either way, extending the Earth's north-south axis, we find an axis for the relative rotation. So this is the celestial sphere, like the Earth, comes equipped with a north and a south pole. In fact, the north celestial pole is the point that you would see in the sky if you stood at the Earth's north pole and looked straight up, and similarly the celestial south pole is what you would see if you stood at the Earth's south pole and looked straight up. And so we naturally have, splitting the distance between them, a celestial equator, which is either the set of all points that are 90 degrees away from either of the poles, or, if you wish, take the Earth's equator, imagine lighting a light bulb inside that Earth there, and projecting the shadow of the equator all the way to the celestial sphere. That gives you the celestial equator. And once we have a celestial equator, we can measure the latitude of a star, again, just as we do on Earth, by measuring the angular distance from the celestial horizon to the star, so that this star here is at a latitude of north 44.7 degrees. We call celestial latitude declination. As I move the star around the sky, its declination will change. Declinations south of the celestial equator are negative, declinations north of the celestial equator are positive. And now, as the Earth rotates, we observe, if we want, as the celestial sphere rotates from east to west, this star will move along this line of latitude, and just as on Earth, we need to add to the specification of declination some specification of longitude. And just as on Earth, we pick randomly a line, a meridian, a projection of some meridian on Earth at some time, a circle that crosses both poles. We call that the zero longitude. Celestial longitude is called right ascension. So this is the zero right ascension circle. It is chosen so that it intersects the celestial equator and some particular star, and in this case, this star is in the constellation Pisces. And so using the longitude of that particular star in Pisces, we call that zero longitude, and we measure longitude east along the celestial sphere away from that, so that, for example, a star might be 90 degrees away. You'd call that celestial longitude 90 degrees, or if it were 90 degrees to the west, you'd call that celestial longitude 270 degrees. In a twist, celestial longitude is measured not in degrees but in hours, so instead of a full circle being 360 degrees, the full circle describes 24 hours of right ascension. That means a conversion rate of 15 degrees per hour, so that a star that is 90 degrees away from the prime meridian, instead of being at celestial longitude 90, will be said to be at right ascension 6 hours. Remember, this is quite reasonable because the celestial sphere rotates from east to west, which means if you're looking overhead and you see the 7th meridian, wait an hour. In an hour, the celestial sphere rotates 15 degrees, and the 8th meridian will be overhead. Wait 24 hours, the celestial sphere will have completed a full 360-degree rotation. You'll see the 7th meridian again. This is why measuring right ascension in hours increasing to the east totally makes sense. Now, before we proceed, there's a technical question we will need to ask, which is, I said the celestial sphere is large. What do you mean by large? Well, the statement I want to make is that we need the celestial sphere to be large enough for this model to be mathematically accurate, that the lines of sight from any 2 points on Earth to a given star can be taken to be parallel. In other words, we can assume that everywhere on Earth is effectively in the center of the celestial sphere, and so in particular, if in this picture these 2 points, say A and B, are 2 different points on Earth, and this point O is the position of a star, I need to imagine that to within the accuracy of our measurements, the line from A or from B to O are in fact parallel, or this angle, which I shall call alpha, is smaller than anything we can measure. The size of the celestial sphere here, representing the distance from points on Earth to the stars, would be represented in this picture by this radius r. So what I need is a relation between distances and angles, and the relation is going to be something we're going to use repeatedly in the class, so let's develop it and understand it. So I have here this circle of radius r about the point O, and where I start with is the formula for the circumference, S, of a circle, and we all remember that the circumference of a circle is 2 pi r. Suppose I want to know the length of this segment of the circle, this arc between A and B. Mathematically, you denote this as AB with a little squiggle on top reminding me that this is the arc. So this is not too hard. Imagine slicing a pie. To figure out how much crust you get, you take the amount of crust in the entire pie and then figure out how much your slice is. Your slice is a fraction of the entire pie, that is the ratio of alpha, your angle, to 360 degrees. This tells you how much of the pie you have, and I multiply that by 2 pi r. And that gives me the arc length between A and B, and if I perform the full division here, this is alpha divided by 360, this is alpha divided by 57.3 degrees times r. Now, the point that I want to make is that if the angle alpha is in fact small, then the difference between measuring the arc length from A to B and the actual distance between A and B, which is the straight line distance along the green line, is very small. And so for small alpha, the distance from A to B is similar or approximately given by the arc length, and this expression, called the small angle formula, is one that we will use very often in the class. It relates distances to angles. I can rewrite it as alpha divided by 57.3 degrees is AB divided by r. So what this tells us is, for example, if we can measure angles with some precision, we need the ratio of all terrestrial distance to the celestial sphere to be small enough that the angle you get from this expression is smaller than the precision of any of the measurements we do. Now, you may see the same formula written with very different numbers. So compare what I wrote to this expression, and they look very different. this brings up another important point that I do not want to miss. Neither of these expressions, of course, is wrong. They're just expressing the same angle in different units. In measuring small angles, we often measure units in fractions of a degree, and for the same Babylonian reasons that give us minutes and seconds, we measure fractions of a degree in arc minutes, 60 of which make up a degree, and in arc seconds, 60 of which make up an arc minute. And if you perform the computation, you find that 57.3 degrees corresponds to this great number, 206,265 arc seconds. So that these two expressions are in fact the same expression. The same angle is written as different numbers of different units, which reminds us that when we're doing physical science, numbers are in fact the ratios of one physical quantity to another physical quantity. If I say that my height is 178 centimeters, that means it's 178 times some fiducial unit, which is a centimeter. And so when we specify a physical property by a number, it's very essential to remember the units in which it is expressed. And often, if you misunderstand the units, you get incorrect answers. And at this point, you may be saying, "Hey, Ronan, what about your consistency? You never specified in this expression units for the length AB and for the length r. Those are two physical properties, and what units are you measuring them? Is that in light years, in millimeters, in angstrom?" And the answer, of course, is that this expression will be correct no matter what units I use for A, B, and R, as long as I use the same units, because remember, one way we wrote this formula was that alpha over 57.3 degrees is AB divided by R. Now we see that on the left-hand side I have the ratio of two angles, an actual number, and on the right-hand side the ratio of two lengths, and the ratio of the number representing AB and the number representing R will be the actual ratio of the lengths, so long as they're expressed in the same units, whatever those units are. But this reminds us, A, that we have to be careful when doing physics. The correspondence between quantities and numbers involves units, and B, that the best way to avoid unit errors is to always write our expressions in terms of ratios of objects of the same unit. Then those numbers are actually meaningful. Here again is our favorite view of the sky from Athens at 9 p.m. on November 27th. And what I've had the software add here in green is the celestial coordinate grid. So here we have the celestial equator. And if we raise our gaze a bit, then we can take a look at the celestial North Pole here. And we see the lines of fixed declination are concentric circles around the pole, and we see the lines of fixed right ascension are the lines of longitude spanning out of the pole, and we see right here the prime celestial meridian, which, as promised, meets the celestial equator in the constellation Pisces over here. And so we have the appearance of the celestial coordinate grid in the sky over Athens, and what we can see is that as time progresses, notice that here we have, I will mark for us, the position of the prime meridian. This is where 0 hours of right ascension is, and then to the east of it, by 30 degrees, we have the 2-hour right ascension line and 4-hour right ascension line, and so on. And the reason that this makes sense is that if I let 2 hours go by magically moving the clock, notice that the 2-hour right ascension line, the sphere having rotated 30 degrees, is now exactly in the position where the 0-hour right ascension previously was. 0 hours of right ascension has rotated over, and so hopefully this clarifies the way in which right ascension measures the rotation of the celestial sphere. To summarize what we've learned in this quick first video, we've learned that we can imagine the stars as fixed on a large celestial sphere, concentric with Earth and surrounding it. The size of the sphere is governed by our favorite formula, the small angle formula. So the angle between the lines of sight to a star, for example, is AB divided by r, where r is the radius of the celestial sphere, distance to the stars. AB is some distance between 2 points on Earth, and we pick r so big that this angle is too small to be measured. The motion of the stars is carried by the fact that the sphere rotates daily from east to west. We measure positions on the celestial sphere by giving declination, celestial latitude in degrees north and south of the celestial equator, and right ascension, measuring from some particular meridian in hours of right ascension moving to the east, and this corresponds to the rate of rotation of the celestial sphere.